And we start, of course, with the webinar today, which is focusing on natural materials for retrofit special windows in this case. Next slide, please. So today's agenda is starting, you had the intro, and we will start with Arnaud Evrard. He will give us an insight into natural interior insulation materials, their building physics, characteristics, and the specific requirements and challenges they pose. After that, we will have an input by Judith Resch. She will share with us the planning and design advantages that wooden windows offer in renovations. We can learn with her how the concept of simple building can be put into practice through the use of wood, of course, and while still meeting high standards. And after that, there will be time for your questions and lively discussions. And the discussion will be held with Arnaud Evrard, Judith Resch, and of course, ETHZ, who is the managing director of the Federal Association of ProHolzfenster. Next slide, please. So starting with Dr. Arnaud Evrard, he is an architect with PhD in engineering science. He was a researcher at the University of Louvain in Belgium. It's the Université Catholique Louvain, as I heard. He was lecturer at the University of Applied Sciences in St. Gallen, and is now senior scientist at the ETH in Zurich. Arnaud, I give you the handover and please give us your input. Thank you so much.
Thank you for the introduction and thank you for the invitation. Also, I'm very glad to be here. I'll share my screen. Only one presenter can share at a time, so you may, yeah, thanks. There. Is this good?
That looks perfect.
All right. So yeah, thanks again. I think you said basically everything. I'll come back on some aspects on the work I did in Belgium and the work I'm still doing now in ETH in Zurich, because I think there's a nice link to this. So my challenge is to be the first. But I think I try to make a nice overview of the main issues we can have with specifically with interior insulation. So that was just an introduction to say, yes, we all know we have to insulate, we have to improve our energy efficiency. The problem is the size of the building stock today is mainly not insulated or very less. So most of the buildings are very low in this. And so the challenge is to bring them up and to increase their energy efficiency. And as you see here, there's many examples of a very nice historic building. Some are not that nice maybe, but there's always also a challenge with heritage value and how to preserve the way they were built and their aesthetic. And so since I started to work maybe 20 or a little more years ago, I always keep on seeing this graphic with the perspective and how we should evolve in terms of carbon emission. So and this graphic keeps on going up actually, and the scenario are always hoping that we will get better. Now the aim is to decrease around 50% of our emission to 2030. Maybe to go to zero emission in 2050. It's very, very, very ambitious, but we do have to try. And I think that's why, okay, we should insulate, but we should always insulate with material with low carbon impact. And that's why I want to focus here on those material, and that's exactly this QR code linked to the teaching we're doing in Zurich. where we actually decided to talk about regenerative material because they're not only good material with very low impact, but they also bring something positive. And in this case, with insulation, we basically talk about bio-based material. So I'll come back on this. So to insulate existing building, we have many choice. We can put the insulation outside or inside. Sometimes there's place in the wall to fill in with insulation. Sometimes there's a wood structure and the rest has to be renovated so we can fill in the structure with insulation. Basically, we'd say when it's possible, when the aesthetic value is not important, insulating by outside is always better. But here we discussed to focus here on inside insulation. So that's what I would do because actually, in many cases, that's the only thing we can do, the best we can do. But the problem is that it's not easy and it makes a lot of building physics problem, or there's like let's say challenges in terms of building physics. So I'm based on a work we did in Belgium, 4-year research on inside insulation on brick wall. So I don't want to say I'm talking only about brick wall, but I think all what we did is actually interesting. So I took some graph and some illustration from there to talk about this. So the inside insulation has a lot of advantage. As I said, you do it from inside, so it's like most of the case it's the only thing possible because you can't put a scaffolder or you can't change the specificities of outside surface. Usually, you don't need a permit, and you can phase the project. So it does have some advantage. But as you can see here, it does also have a lot of risk or disadvantage. And I will highlight these risks, what I wrote in red here, because I think that's what you should keep in mind when you design an internal insulation system. You have to think about all these problems, and there's quite some complexity, as I will try to show, but it's not impossible, and we do have the material to answer this. So for those who has no idea or just to have this main idea, if you insulate your wall from inside, basically your wall afterwards will be colder. And that's what you should keep in mind because that's where all the problem or all the issues are born. So if you look this graphic on the amount of humidity the air can hold depending on the temperature, so the Molière diagram, you can see that if you have some air at, let's say, 20 degree, 50% humidity, which is an average for inside the ambience, as soon as this air would be in contact with a colder surface around 10 degree, there will be condensation. It will be saturated, it will condensate. So this can happen in the wall, on the surface, and of course, that's what we try to avoid, or at least we try to manage. So the biggest risk is internal condensation. So as I said, you have your inside insulation, and your wall outside is colder. So if the vapor that you produce inside or the higher vapor pressure from inside has the tendency to go through the insulation, if there's nothing made to break it or to slow it down, it will most of the time condensate there, and that's a problem because you will have a source of humidity and you can have many other problems linked to this with mold or whatever. So the solution would be to put a membrane on one side or to have a layer with a higher SD value, so a higher break for vapor diffusion. Second risk, which is not so often thought about, is that actually in summer, when the vapor transfer can turn around and go back to inside, if you put a membrane with a very high SD value in the inside to avoid the previous risk, then you may have the other risk that when the wall wants to dry out, he will be condensating on the inside surface. It sounds strange, but it does happen. There's a measurement from Fraunhofer Institute on this. So what you have to do is basically to choose your membrane or your layer inside with the right SD value, not always the highest. It has to be the right one. And for this, which is very good, I am not making any advertising here. There's other product, but basically the smart vapor membrane, like those from Proclima, are really interesting because they do have a different SD value, so a different way to break the vapor transfer depending on the season, let's say. So in winter, air is a little drier. There will be more of a block to vapor transfer. And in summer, where it has to dry out, there will be opening. And so that's a first very good choice, I think, to go in this kind of membrane who are smart. Another risk also linked with condensation is actually you have to manage the air tightness, because as soon as you put a layer of insulation, if you don't manage where the air from inside is going, or eventually the air from outside, why am I holding my hand? Again, you may have a lot of condensation also because the air transport a lot of vapor, and so this has to be managed also because of the thermal performance. So another type of risk is, as I said, the wall will be more cold and actually more wet also, because when it's getting wet before insulation, it can, because it's warmer, it can dry faster and it can dry both sides. If it's insulated inside and if your layer inside is not that open to vapor, the water it's harder to evaporate the water, and it only on one side. So these two things, that more wet, more cold, can bring some frost degradation, so frost problem, which were not there before, and some salt migration, or like improve them. If they were there, or if they were not there, they could appear or they could get worse. So that's a very classic problem with inside insulation on some type of masonry. Of course, if you insulate from inside, you have also to manage the thermal bridge. This is quite obvious, but important to say. As soon as you have electric or something where the insulation level is not that high, you may have a very cold surface where there could be condensation on the surface, on the ceiling or around the window. And there will be condensation because a lot of the vapor, because it can't go somewhere else, will go there and will condensate. So you may have a more problem than before. And the wall is colder, as I said. So that's all the risk you have to face, and you have to combine them. The problem is that we usually, or still, let's say, it's evolving, but we are still using a very simple model, the Glaser model, which basically you just give the thickness, the lambda value, so thermal conductivity and vapor permeability, and with this, in static, he will say, oh, there will be condensation or not. So basically, if the vapor pressure is higher than the saturation pressure, vapor pressure, it will condensate. So that's the software will say, oh, it doesn't work. But as soon as you have inside insulation, you can try it out. It's most of the time it doesn't work. So most of the time, this type of model will tell you it's not working, and then you will put a membrane in front to avoid this. But as I said, then you can provoke some summer condensation. So these models are actually static model, and they are limited because they don't consider how the moisture can redistribute and how it evolves in dynamic in the time. Maybe it's happening not so often, or if it's happening, maybe they have time to redistribute and to re-evaporate. So these models are actually not fitting, and we need some more evolved models. So not everyone has to do WUFI simulation or equivalent. There's MOIST, there's different software, but the best would be actually to make a transient simulation considering all the transfers, a dynamic transfer in terms of temperature and humidity, vapor and liquid water. So it sounds complex like this. I'll try to wrap it around. The thing is, to do this simulation, we need a lot of parameters. Usually, you know, the density, thermal conductivity, and mu value from material, not so much more. In this case, you would need absolutely to have all the other parameters, also the specific heat from the material, each material, also the absorption curve. So basically, you can have a different value to draw the absorption curve. And the absorption coefficient is actually the liquid transfer. You need the absorption value, but you need the redistribution value. So you need a lot of parameter from each material you're using. And so I engage all the material producer to measure this material. Of course, it has a cost, but this helps to be able to simulate and to use the material on the right place. So it sounds complex, but the good news is that the models are there. We can use them. The material parameter, if they don't already exist, they can be measured, or at least they can be assessed. You can always think of what would be the parameter if you compare to equivalent material. So it's possible to assess these parameter. And the other very good news when we want to insulate with natural material is that actually these materials have some specificities in terms of hygroscopy. They are able to have water and to release water, and they can be a good insulation. So they have actually all the parameters, all the properties you need to make inside installations. So my way to think is that natural material are actually more appropriate on the inside as the classical other material or synthetic insulation. So for me, it's a good news. It means that we can use some of those material. And I can't go through all the way to do this. I just try to structure it in 4 different structural system or like constructive systems. You may have some panels where are a little more rigid, could be wood fibers or hemp fibers, and you just put the panel, and on the panel you can plaster. You have the system where the insulation is too soft, or you want to blow in this insulation with cellulose or with straw, and you blow in this wood structure, and on the top you put some earth board or wood board or whatever puts triggers for the plastering. You have this insulation which are kind of a light mortar like lime hemp or earth hemp or light earth mix, and then you plaster them. Or you have these any kind of insulation that you could actually put behind another layer of brick or of masonry. So all are possible with different material, and of course the aim is to have a very nice inside environment, and then again natural material are very interesting to make a very comfortable environment, but it doesn't give any limit on the quality of the insulation that's behind. So I did my PhD on lime hemp material, so I always like to talk about it. Now I'm developing, or like I'm very curious of the development of earth hemp products who are coming, because they have even a lower carbon impact, but relatively the same properties. And why are they so interesting for inside insulation is because they are very open to vapor. They are able to absorb a lot of humidity before any properties can change. And they have this capillary actions where the liquid water, if there is, will be very fast redistributed and re-evaporated somewhere else. So I think these materials are very adapted for inside insulation. I do like a lot straw insulation. Maybe for inside insulation doesn't fit as a straw bale, at least because it's too thick usually, because one of the big problem of inside insulation takes place from the inside. So you may not want to use a straw bale, but still there is some panels, straw-based panels, or these very isostro, these straw that you blow in the wall. So they are very low impact on energy or on the carbon, very low carbon content. Oops, sorry. Oh, I'm bad with the time, so I'll go a little through this. I don't want to go actually through all the material. I think natureplus is a very good place to have a panel of material and to have also a value on how good they are. There's so many material possible that you can't say you didn't find any. There is some. I wanted to finish just by giving a short example. Maybe we can talk about this more in the discussion and come back on some of those slides. The idea is like the building physics behind is quite complex and it depends on many aspects. So that's the strategy we developed in the document I told you about. Always you have to know a lot about the existing building and a lot about the materials who are in this existing building, which usually you don't have if it's a very old building. So there is some test to find out the basic material properties, vapor permeability, liquid absorption, and stuff like this. So you first have to really know good your situation. Is there already frost problem? Is there already salt problem? If there is not, maybe they can come, but at least you have to know, and different orientation are very different. So you have to observe the existing building before taking some choice. And then you try out a solution depending on the budget and the client and the project. And then you have to test this solution and see how good they are. Eventually go back a step and do it again until your simulation are good. Afterwards, it's not finished. The best is actually to follow up the implementation, because the way you build it, if you are not good in airtightness or if you didn't put your vapor barrier the right way, could be a big problem. So you have to be on the building side and check how it's done. And eventually, the best would be also at the end to control how good it's working and to have some measurement. So this case study is a very old heritage building where the architect contacted us to see if they could insulate with cellulose this building. Uh, it's a brick wall, and they want to make a house about it. And so I just show a little strategy how we thought the problem. So analyzing the material, existing material, that's the main thing, as I said, looking at different place where the detail will be different because the wall were not totally straight. And so we developed different kind of detail, and each of them we did this simulation. Of course, there's a brick wall, there's a stone under construction. We had to choose the stone. So we took from the database different kind of stone, and we tried to see what would be the right parameter for this wall. And yeah, the liquid transfer is very important, even if it's very often neglected. And show a lot of graphic, but basically you always have to look that the moisture of the wall has to go down with the year, or at least stay stable, and it should not go too high. So if you see some curve like this one where the moisture content of the wall goes up, it's not good, because at the end the wall will be full with water. So depending on the vapor barrier, depending on the parameter of the material you choose, you look how it's going to work on the long term. Of course, you have to be careful of some details where the beams are going in the walls, etc. I think maybe a last thing is something what was a surprise for me is that the orientation of the wall and how much driving rain is going on the wall was one of the main parameter actually. If the wall was painted, it could not dry really good, and so we had some accumulation problem. And so there was no rain, of course, you don't have the problem, but as soon as you have rain, you do have to have a layer who's regulating the liquid transfer, so lowering the liquid transfer, but still not lowering the vapor transfer. So the wall should be open to vapor, but should be close to water. So basically, that's what these graph says. So to conclude, just like you can build with almost any material, can build with straw. Maybe what you have to remember of the story of the three little pig is that you should not ask a pig to build your house. So it's in the detail in how you build, how you manage the air tightness, how you manage the vapor tightness, and how you manage the drying potential of the wall. The wall would be able to dry if it's wet.
Okay.
That was a challenge. Sorry if I went a little over the time.
No, but you're fine. 20
Perfect.
minutes, you're good in time. And we still have another 10 minutes to go for discussion. So this is, thank you, Arnaud, for this
Welcome.
very complex and, of course, difficult topic. I know, and we always know that this is something which is driving you mad if you have to think about in insulation inside and so on. So before we open, I would have one question. Did you what kind of okay, the material issue is one of the for the indoor insulation would be one kind, and our products like natural sound materials will be good choice, better choice than any plastic or whatever you can use, insulation made out of fossil fuels and so on. But one question which is also coming up is what about technical solutions like ventilation? What is your opinion to that? Is that helpful, or it's not in the kind of a low-tech building or low-tech working prognosis, but is that good, or would that be other hindering on that?
What we observe is that ventilation make, makes it you're able to discharge a lot of vapor through ventilation. So if you have a good ventilation, you're normally able to lower your humidity level down. So basically, of course, ventilation is anyway good to bring fresh air, but it's also good to regulate humidity. The thing is that if you have material who doesn't have any capacity to regulate humidity, you have to do everything through the ventilation. And then you need usually a double flow ventilation, or you need a lot of systems somehow around this ventilation that you could actually make it much more simple if your materials and your walls are helping on the humidity regulation.
Okay.
So I would say ventilation is very important, but because you have materials inside that are able to regulate humidity, could be a not so a big problem.
Okay, thank you. Architect and carpenter, and she studied in Munich, and she was a scientific research associate at the Technical University of Munich with Professor Nagler, I suppose, who is one of the low-tech pioneers, I think. Has been lecturer at the School for Wood and Design in Upper Bavaria, and now she is lecturer on architecture at the Technical University in Rosenheim. And of course, not to forget, she wrote a wonderful book on low-tech buildings with wooden windows. So look at it. It is worth reading, I think. And dear Judith, the stage is yours.
Thank you. Thank you. Good afternoon. Thank you for the invitation. It's a privilege to be here for me. And I want to talk about windows, wooden windows, a subject which I've been working on and passionate about quite a while. You can see my presentation now. Is it right? Yeah. Windows, you all know, are exposed to the elements and especially today need to meet high expectations. And you need to be a little bit brave to design your own windows. But windows are signature elements of a house, and it's worth to have a little bit courage working on windows. So I want to show you 4 different wooden window projects. I want to show you the potential of wooden windows. The first 2 projects are examples of energy refurbishment of existing wooden windows. The third project exemplifies why wooden windows are sustainable, which is linked to both design and material as such. And the last project shows us how the design of a wooden window enables a more simple technical setup of a building. For me, as an architect, it is important that windows are considered as a part of an overall design concept. So here, the first example is about the windows of a typical farmhouse in Upper Bavaria. This is a listed building from the 19th century, and it stood empty for a long time, which has helped to keep its originality. While the other facades in the row of the houses on both sides of the street were renovated, this house was not touched. For that reason, the windows and the doors from the 19th century stayed preserved. Here you can see a window, and you can see that it is from pre-industrial times. Well, the owners planned to restore the house, but they were unsure how contemporary living comfort could be created in this house. They were especially concerned about the windows. In order to show that it is possible to enhance the windows, I proposed to build a sample. So the proposed solution was quite simple. We introduced a second glazing behind the historical window at the inside. The 2 windows, the new and the old one, form a box-type window together, which gives considerably better protection to cold and, that plays very important, to sound. Yeah, here the drawing. This is the old window, and here's the new layer. And here in the horizontal section in detail. This picture shows the window construction, and here the inner frame has just been assembled. And this links to the question we were just discussing. We had 2 different ways to treat the inner reveals because of the facade. The Monument Protection Authority required us to historical plaster at the gable facade. Hence, we decided to treat the facades in different ways. At the north facade of the house, we decided to put this wall heating from copper pipes into the reveal. That's because we had to restore the north facade, the gable wall with the most parts of the historical plaster. That was this facade. While we put new mineral insulating plaster on both eave sides. So that was the agreement with the authorities. Our concept of the box type window was agreed during the planning phase with a building physics consultant. And here you can see the technical specs. So the U value is of course now much better, but not as good as the U value of the masonry. And here you can see that the protection from the noise is also much better. The new parts of the window were made in a craftsmanship way, in the manner of the historical windows. And what it was impressing, most of the historical windows were still functional. The surface was damaged, and some parts of the window frames were damaged. But so we replaced them, as you can see here on the drawing, or for example here, you can see the replacement of wooden glazing bars. And these new parts should be made out of old wood, for example, from old window parts, because practice has shown that the wood from old window parts is more durable. The paint of the window was removed in a thermomechanical way, and the surfaces were coated with a linseed oil-based paint system. This method has been tried and tested for centuries. It is natural and very durable because it penetrates into the wood pores and remains elastic. But it takes days for it to dry. And here you can see a sample of a part of the facade, including the window. Finding the color concept is a process, and it takes time. In the construction, we found different historical colors, and this inspired the choice of the color of the windows. And here you can see the facade nearly finished. Here. The preserved windows critically define the appearance of the renovated building. And while the owners initially were reluctant to agree to the rework of the windows, they are now super happy about the result and proud about method of restoring the building. Let's look at the next example. So what about this window? It's a composite window of the 50s, and the insulation is not up to date. It is part of this house, which is of course not listed. And the house, it looks unobtrusive, but if you take a closer look, you can find a lot of remarkable details. There is a north facade with a regular rhythm of windows of the same size. And there is the entrance with this slightly curved stair landing. And here you can see the architect's drawing, which are made precisely in different scales. And for example, here the cellar door. Again, the north facade, look at the windows. They are fitted flush with the facade, with a surrounding shadow joint of constant width of the wall opening. And here the slim grills of the ground floor windows, which are also integrated flush into the frames. And this is an original drawing of the window details that shows that it's very well considered. And here you can see the elevation and vertical section of this window. It was enchanted by the design of this house. On the flip side, the heat transfer of these nicely designed windows is immense. So here you can see the thermal image of the facade. The weak points are obviously the glazing and the reveal. The heat loss at the reveal is caused by a steel frame where the windows are attached. So this is the the steel frame, and this is the vertical section in detail. Yeah, for very good reasons, the owners wanted an inert energy refurbishment. So, of course, we discussed the replacement of the windows. We made some drawings with contemporary profiles, but we did not find a satisfying solution. So we came back to the original windows and decided to improve them and also the reveal. But the steel frame here also brings about an advantage. The window can be removed easily without damaging the plaster. So to see if it works and how it looks inside, we removed one window, as you can see here. Here's the steel frame, here in detail. The removed window. Yeah, now knowing the situation, we developed a concept for improving the windows and the reveal. Here is our plan. So we replaced the second glazing with a new one, a vacuum glazing, which is much more efficient. We made grooves routed at an angle into the rebate to fix seals. And we planned interior insulation for the interior reveals. Yeah, and after refurbishment, a cold winter challenged our windows. And the outer glazing was so cold that the snow did not melt because the inner glazing insulated very well. The insulation of the reveals is not yet installed. So for now you still see some heat loss here on the thermal image. Here, this is the old situation, and this is the new one without yet insulated reveals. Yeah. Here you can see the cross-sectional area of a conventional energy refurbishment compared to our concept. So we could minimize the material consumption and retain a significant energy consumption. This project exemplifies that it is important to take equal consideration of thermal insulation and the architecture of the building. So now you might argue that these examples are quite peculiar and not mainstream architectural projects. In most retrofitting of building shells, windows will be replaced. Then the question comes down to the material of the new windows, wooden windows versus plastic windows. For this debate, I want to give you some arguments why wooden windows are more sustainable. As we just could see, wood is easy to work by hand and can be simply maintained in the long term by replacing any damaged parts. And the material's physical properties of wood, such as thermal insulation, load-bearing capacity, temperature-induced dimensional changes, and electrostatic charging or discharging, are much more favorable than other materials. In case of fire, wood is considerably more resilient than, for example, plastic, because wood burns more slowly, emits no highly toxic dioxins, and does not melt. And of course, wood is not a special waste. And many historical examples show how durable wooden construction can be. So now I want to go on with an example where the challenge of developing a new window for an existing building was solved in an exemplary manner. This window was developed in cooperation between architect and joiner, building upon the tradition of wood craftsmanship. They aimed to meet high standards of heat insulation. The original windows of this former farm building were not preserved, and that's why the architect wanted to design new windows. The frames should be as slim as those of historical windows, but accommodate a modern triple glazing. And here's the result of the project. They designed a window as precise and fine as furniture. Let me show you the construction. This is the vertical section. You can see the historical wooden wall with the outer insulation, with a new slim window, with shutters enclosed by a frame. And here's the explanation why the frame is so slim. So the fitting of the window and the glazing is arranged in two different levels, opposite to conventional design. And here you can see that the weather bar and the other lower parts of the construction are made in oak, while the other parts here are made of spruce. And here you can see it in detail. These are the oak elements, and this is in spruce wood. And it is even possible to replace some parts of the construction. For example, here behind the seal, there is a screw that can be removed easily to attach, for example, a new weather bar. Yeah, so my last example is, right? I don't know, I can go on. Yeah, here. My last example is traditional and simple and modern at the same time. The house was built in comparison recently, and it is used as a presbytery. And the windows are an integral element of the architecture. They are also box type windows, and like traditional winter windows, which is also typical for our region here in Upper Bavaria, they have outward opening casements. This is possible because of the wide roof overhangs and balconies that protect them effectively from driving rain. In warm weather, building users need windows that are simple to open. So this is the summer version of the windows. In winter, both casements are closed, but there are variations. Here you can see both casements in a horizontal section. It's a box type window as you know it, but look at this vertical section. If both casements are closed in winter, there is a controlled amount of fresh air coming through. in between the glazing, the air becomes warmer and flows into the house. So, how does it work? Let's have a look on the details. At the lower part of the outer casement, the seal is missing. So this little gap is the reason why the air can float between the glazing. At the upper part, there is a perforation where the air can get into the house. So, but you can also close it so that there's no air coming into the house. Here you can see it, and here inside. Air changes can also be controlled and regulated by an additional mechanical exhaust air system. The state moisture-laden air is extracted from the area at the back of the building, for example, from the WCs. Fresh outdoor air streams in to replace it, because extracting air from the building reduces the indoor air pressure. For this to work requires free passage of air through all rooms, which is provided through adequately dimensioned gaps at the doors. So the window is a part of the air change in the building. The different opening variations of the inner and outer casements allow the ventilation of the modern box-type window to be precisely controlled while providing good thermal insulation. And the components, look here, are quite simple. So due to this intelligent, aesthetic, and simple design, this house gets by with little building technology. So you can see that designing wooden windows means a lot of possibilities for the appearance and function of a building. If we want to create good architecture and take the aspect of sustainability serious, we should not forget to put a special attention on the design and construction of windows. Yeah, and if you're interested in further details and further projects, have a look into my book, where you can find a lot of drawings. Yeah, thank you for your interest.